Welcome to The Explainer. Today, we're diving into an absolutely fascinating breakthrough regarding how artificial intelligence actually processes massive, sprawling amounts of information. If you've been following the rapid evolution of autonomous AI, you know that search agents are taking on increasingly complex tasks, but you might be wondering, how do they keep track of it all without completely losing their digital minds? Think about it like this. Imagine trying to work on a really complex research project, and you're trying to keep, say, 100 different browser tabs open at the exact same time. You've got PDFs, news articles, data tables, search results, all just staring back at you. Eventually, your working memory hits a wall, right? Well, what happens when an AI reads too much information at once? It literally faces the exact same problem. It forgets, it gets completely overwhelmed, and worst of all, it hallucinates. When an AI agent runs a long horizon search, its working context just explodes. And if it tries to hold on to every single thing it reads, we're not just talking about a minor little glitch. We're talking about drastically increased computational costs, skyrocketing error rates, and totally broken chains of reasoning. Okay, so let's dive into this. Here's our roadmap for today. First, we'll look at the search agent era. Second, the context bottleneck. Third, elastic context orchestration. Fourth, we'll cover 5 tools for memory. And finally, how LongSeeker takes the lead.
Section 1. The Search Agent Era.
So we have moved way beyond the days of just typing simple keywords into a search bar. The real foundation of modern AI capability is something called the React paradigm. Basically, it's an iterative cycle where an AI alternates between reasoning about a problem, executing an action, and then integrating the observation. It's a brilliant system, but as tasks get longer, it hits a massive hidden mechanical limitation. And right now, everybody is racing to perfect this paradigm. From top-tier proprietary labs like OpenAI to the open-source teams pushing the boundaries, agentic search is basically the holy grail. But the wild part is that all of these systems, regardless of who builds them, are running headfirst into the exact same wall. Section 2. The context bottleneck. Let's look at what's actually happening under the hood when an AI searches the web for a long time. Most models today use what's known as naive accumulation. They just keep appending every single intermediate result to their memory log. As you can imagine, this quickly creates a super noisy, redundant, and overloaded context window. What the system actually needs is true working memory. Curated, highly relevant information that maintains reasoning continuity without all that extra noise. Now, engineers have definitely tried to fix this with a few band-aids. There's sliding window truncation, which honestly just cuts off old information blindly, ignoring what's actually important. Then there's threshold-triggered restarts. These suddenly clear the memory, which severely disrupts the AI's train of thought. And periodic summarization just loses critical details, building up abstraction errors over time. The bottom line? None of these give the AI precise, on-demand control over its evolving context. Section 3. Elastic context orchestration. This is a massive paradigm shift, and honestly, it's incredibly exciting to see how elegantly this solves the problem. It's called Context React. Instead of just passively receiving information, we're giving the AI the power to actively manage its own memory. So at each step, it jointly produces its reasoning, decides on context meta-operations, and makes its next tool call, all in a single pass. It actually gets to decide when, where, and how to reshape its working context. The core insight here is that information needs to exist in different forms as a task evolves. Think about it. Fresh evidence might need to remain totally intact so it can be verified. But once an issue is resolved, that data should really be distilled down to a simple conclusion. And if the AI goes down a completely failed rabbit hole, that entire branch should just be wiped clean. This kind of state-dependent fidelity is the absolute key to maintaining perfect detail without the bloat. Section 4. 5 tools for memory. So, how does the AI actually pull this off? Well, researchers designed a meta-operation vocabulary. It's basically a brand new mental toolkit for the agent made up of 5 atomic actions: compress, snippet, delete, rollback, and skip. Before the AI even adds a new observation, it uses these tools to dynamically clean up its past. Let's break these down. First step is compress. This replaces a long, drawn-out range of past steps with a tight summary. It's exactly like summarizing a 2-hour meeting into just 3 bullet points. Second is snippet.
This one is crucial. It preserves exact precision-critical substrings, like specific numbers, entity names, quotes, or lines of code, so they don't get distorted when things are summarized. And third is delete. If a step no longer carries any residual value, the agent just mercilessly throws it in the trash. Together, these tools explicitly cut down generation costs and drastically lower the risk of hallucinations. Rounding out the toolkit, we have Rollback and Skip. Say the AI realizes it went down a bad path. Rollback lets it abandon that unproductive branch. It reverts the context back to an earlier state, but, and this is vital, it records why it failed, so it actually learns from the mistake instead of just repeating it. Finally, Skip simply leaves the context unchanged if things are already compact and informative. Researchers note that the compress tool alone is technically expressively complete, but giving the AI all 5 of these specialized tools guarantees top-tier efficiency and fidelity.
Section 5. LongSeeker takes the lead. Okay, so we have this incredible theoretical architecture, but does it actually work in practice? To test it, the researchers built an agent called LongSeeker. It was fine-tuned from a QN3 base model using 10,000 synthesized search trajectories, and it was trained specifically to use this active memory shaping. And the benchmark data brilliantly illustrates the impact. On the highly challenging browse comp evaluation, LongSeeker stands completely tall, beating out a serious lineup of top-tier foundation models and advanced search agents. It achieved a staggering score of 61.5% on browse comp. To put that into perspective, you can contrast that directly with other really competitive, long-horizon search baselines. For example, Tongyi Deep Research scored 43.4%, and AgentFold scored 36.2%. By actively managing its context, LongSeeker just blew past them. And it's definitely not a fluke. The rigorous Xbench evaluation proves that LongSeeker's success is incredibly consistent. Across multiple representative benchmarks, including a massive 62.5% on BrowseCompZH, this elastic context method works beautifully. Which brings us to the core thesis of this research. To quote the team directly, agents could achieve more reliable and efficient long-horizon reasoning by actively shaping their working memory. Context management is no longer just some peripheral engineering trick. It is an absolute core component of how an AI reasons. Which leaves us with a massive question to ponder. As agents are deployed to solve ever more complex, multi-day or even multi-week tasks, will this kind of active memory shaping become the foundational standard for all future autonomous AI? It certainly seems like the context bottleneck has finally been cracked. Thank you so much for joining me for this explainer. I hope it helped you understand the incredible mechanics driving the next generation of AI search.